So when we speak of minimum solvent flow and optimum L prime to V prime ratios, the optimum L prime to V prime ratios is actually still based on the minimum solvent flow. So if you recall our discussion in gas absorption and stripping last semester, we first determined the minimum solvent requirement, and from that minimum solvent requirement, we determined the optimum flow rate that is required. So the range that is suggested in your handbook is 20% to 50% more than the computed solvent requirement. So this is in the case of, this one is for extraction. So V is our solvent. Now, in our case, since this is a range, we will use the maximum value that is placed in here in the range. So we determine the minimum requirement for the solvent, and we multiply it by 1.5. That would be our optimum solvent requirement. Okay. Now, in John Copley's in figure 12.7, the 7, page 798, you have there the illustration on how to determine the minimum solvent requirement for stripping. That's for stripping. The same applies for extraction, because in the case of stripping, we're taking out a component of interest from a liquid. In the case of the extraction, we're also taking out a component of interest, or the mass transfer is also from a liquid. The only difference with stripping is that we're using a gas solvent. In the case of liquid-liquid extraction, since it's liquid-liquid, our solvent is liquid. So in the sense, that's the only difference. But the manner of determining the minimum solvent flow rate is still the same. So I'd like to show to you that figure. In the original set of slides, it was not included. So I included it here for ease of explanation. Now, this is the figure that I'm referring to. So if this is stripping, so the optimum solvent requirement will be based, as I've said, on the minimum solvent requirement, multiplying it by 1.5. But the question is, how do you determine the minimum solvent requirement? So if this is your equilibrium curve or line for your system, so you achieve this particular, or you get this particular curve by plotting the XY equilibrium data if provided. If not, then this particular diagram should be made available. The operating line is of course found below the equilibrium line or curve, because it's stripping, or it's taking out a component from a liquid phase. So the operating line is below. So if we want to know the minimum solvent requirement for our extraction process comparable to stripping, there's a need for us to determine the Y2 maximum. Now, how do we determine the Y2 maximum? So with the X2 that is provided in the problem, you will multiply it with the slope of the equilibrium curve or line. Now, if the problem does not give us the slope because our curve is curved, meaning the slope is not constant, then there's a need for us to really refer to a diagram, project the point that you have plotted for the pair X2, Y2 given in the problem, or probably one is determined given the other. So if this is the point, you project it up until you have already its projection on the equilibrium curve or line. Then you determine the slope of the curve or of the line on this particular projected point. There's no need for you, of course, to do the projection if you have an equilibrium line, because most of the time the slope will be provided by the problem if it's a straight line. The only time that it's not provided is when it's not straight, meaning the slope of the curve is varying because it's a curve. So that's the time that there's a need for you to plot the curve and then check the projection of this point having coordinates x2, y2 on your curve. Now the question is, where is point 2 and where is point 1? So we go back to our tower. Our representation using McCabe has 1 labeled for the streams below the tower and 2 for the streams on top of the tower or your column. So then this X2 is this one, the weight fraction of the solute in the feed, because we have the feed being introduced on top of our extraction tower. I am using the term weight because in extraction, that's another difference with stripping. In extraction, we're using weight percentages. In stripping, we're using mole fraction. So this is weight fraction of the feed, and given the slope of the equilibrium line, or knowing the slope of the curve, you'll be able to get your Y2. And this is already the point wherein you have the corresponding minimum solvent requirement. Now, what's the essence of having to find this point Y2 maximum? I'd like to, this one. So when you do your component balance, it is always suggested, again, review, it is always suggested that when you determine the minimum solvent requirement, you use the inert streams, the ones in which you have the L prime and the V prime equation. In there, since we're talking about extraction, you will have to determine the V prime minimum, because the V prime minimum is our solvent in the case of extraction. With this two, with this Y2 maximum, or using this Y2 maximum, you determine the V sub 2 minimum, or simply the V prime minimum, because your V prime minimum would be the same even if we talk about V1 prime minimum or V2 prime minimum. Since we're referring to the same inert stream, then that's the same. Okay, so if you have your notes on stripping, that's the same thing. You use the component balance equation in which you are making use of the L prime and the V primes, and determine the V prime minimum. Why am I emphasizing this? Because you can't find a sample problem that is talking about this particular application in Jen Couples or in McCabe. They don't discuss it. They simply discuss in a single paragraph how you're going to go about determining the minimum solvent requirement, because it's parallel to the topic that has been discussed, which is stripping. Okay, so that's the way you're going to find the minimum solvent requirement for extraction. Determine the Y2 max, that way you can have the V prime minimum. Then after that, you can determine the optimum solvent requirement. That's in the case of extraction. Okay, so again, this is 1 and this is 2. And you have this projection here to find the Y2. Don't determine the V prime minimum if you don't know the Y2 maximum. It has to be, this one comes first before the V prime minimum. Okay, now let me just clear the markings. Okay, now in your handbook, on the other hand, what's available? In your handbook, there are equations that help you solve for the minimum and maximum solvent to feed ratios. It's just like if you have already the feed, what would be the minimum solvent requirement for such a feed, or what would be the maximum solvent, requirement for such a feed. These particular equations are in this particular part of your handbook, section 15-23. I was not yet able to check it with the 9th edition because what I've indicated here is the 8th edition. So if it's available in the 8th edition, I'm sure it's still on the 9th edition. What they do normally with the current edition is add things rather than delete. So these are your equations to use. Read, it's very important that you read the definition of the variables or the parameters that appear in the equation, because the handbook has different definitions for the variables or parameters that it is using. Just like the equation that I have shown to you on how to determine the theoretical number of stages using the available equation in the 9th edition. It's different than the one we have in Jen Couples and even in McCabe. Now, very important is this. This does not require that you have the equilibrium data or the equilibrium diagram. This does not require that you know how to plot the equilibrium curve or line. This does not require that you know how to plot the operating lines. It simply is using the equation E is equal to K sub D V over L. Now, I have sample problems here that will be using this particular equation, the E, and this will be used in determining the amount of solute that remains in the feed, or the recovery of the solute by the solvent, or how many number of stages is needed for such a given recovery. So, the use of the formula is straightforward. Magsing na ko gani nga straightforward hapos, as long as kabalo ka kung ano ang gina-represent sang ara sa mga formula. The E is the extraction factor, the K sub D is the distribution coefficient, the V is the solvent, and of course the L is the feed. If we have a single extraction unit, the fraction of solute that remains after using, take note, after using a pure solvent. So meaning this formula will not apply if the solvent that you're using has a certain amount of your solute. So in a single stage extraction using a pure solvent, after one extraction, this is the amount remaining, the solute that remains unextracted by the solvent. So remaining in the, of course, in that case, that would be already your raffinate, kay why na siya makuha sa imo nga solvent nga magwa siya as extract. So nabili na siya, ato na siya sa raffinate. So this is the formula. Okay, it will use the E, the extraction factor. As for fraction of the solute recovered, this is remaining, this one is recovered using pure solvent. So the opposite of this one, this is the formula. So E over 1 plus E. Now, in McCabe 7th edition, because I'm not sure with the other edition, this is found in equation 23.4, page 779. The use of these equations are seen on example 23.2, page 780. Now, since I say the application of this particular formula is straightforward in this particular example, I leave that to you to read. So what I'm going to give you this afternoon is a different set of problem other than the sample problem that you have in McCabe that will be using this particular set of formula. Okay, so you have the sample problems here. So I have 3 in here. So solve problems in liquid-liquid extraction. Now, in sample problem number 1 here, you're given a solute that has an extraction, a distribution coefficient between water and chloroform. So your system is water chloroform of 5. Telling you that the KD is already equal to 5. Suppose we extract a fifth. Okay, wait. You don't see? Miss, wala ko show ang problem. Okay. As expected. I will just share again. Okay, you share. Where is it? Do you see it? Can you see it? Okay, thank you. Where was I? So I read again. A solute has a K sub D, your distribution coefficient between water and chloroform of 5. So KD is equal to 5. Suppose we extract a 50 ml sample of 0.050 molar aqueous solution of the solute using 15 ml of chloroform. In this particular statement, I'm already reading the second statement. The 50 ml here is the amount of the feed. So this is L. Okay, L. Suppose we extract a 50 ml sample of this concentration of your solute using this organic solvent, which is chloroform. This is L, 50 ml. This is V, 15 ml. So you have the KD, the L, and the V. What is the separation extraction efficiency? Or what is the extraction efficiency of your separation? What volume of chloroform do we need if we wish to extract 99.9% of the solute? Okay, so this is Letter A is asking the efficiency. And letter B, given the efficiency, what volume of the solvent will be used to accomplish such efficiency? So now, in terms of the fraction of solute that remains in the feed, you have it L over KV plus L. This is the unrecovered solute. So the formula will be again a substitution thing. 50 for the L and 15 for the V. The 5 is for your K or your K sub D specifically. If the fraction of solute remaining unextracted is zero point 0.4, then the extraction efficiency is 60% because you still have zero point 0.4 that remained unextracted. So your actual answer for this one is 60%, not the 40 that you solve using this particular formula. Okay, now letter B. What volume of chloroform do we need if we wish to extract 99.9% of the solute? Volume is equal to the extraction factor or the extraction efficiency times the feed divided by the quantity 1 minus the extraction efficiency times the distribution coefficient. So this is a formula that was not presented there in the previous slide, but rather you can derive this particular formula from the set of the three formula that only McCabe shared. It's not found in John Copley's. So, but nonetheless, this is the volume of the solvent that will affect the efficiency that is stated. So this is the 0.999, the efficiency. The feed amount is 50 ml. So 1 minus 0.999 times the distribution coefficient. So to achieve 99.9% efficiency in recovery, you need 9,990 ml, or that would be 9.9 liters of chloroform. That way, you will have 99.9% extraction from a feed that is 50 ml in volume and having a distribution coefficient for the system water chloroform of 5. Okay? Now, number 2. In number 1, so meaning I'm still using this particular data here. Determine the extraction efficiency this time for 2 identical units. What about for 3 identical units? What would be the corresponding extraction efficiency? Remember, class, this one that we solve here is just raised to 1. The L over KV plus L is understood to be raised to 1 because this is just for a one extraction system or a single extraction system. If you make it generic, if you want a formula that is generic for n extraction system, this rational expression should be raised to n, where n is the number of extraction systems. So this is what we're going to do here. Okay? For 2 identical units, for 3 identical units, you use the same formula, but of course you raise it to 2. If you have 2 identical units and 3 for 3 identical units. So what is this formula? This is the fraction remaining, just like this one, the fraction remaining. This is not yet the efficiency, so you have to subtract it from 1. So this is the fraction remaining for your solute for a 2 extraction system in number 1. Same feed amount and same distribution coefficient and solvent. So 0.16. So your efficiency is 84%. What about if it's 3? So your unrecovered is only 0.064, or that's 6.4%, giving you a much higher extraction efficiency, which is 93.6. So take note of that formula. They are straightforward, easily asked in a multiple choice manner. Okay? Now, to determine the extraction units that will give you 99% efficiency, then you will have 1 minus E. This is your formula here because actually this one is the unrecovered. So if it's efficiency, you want the recovered. So that would be 1 minus E. 1 minus E is equal to 1 minus 0.999. This is your efficiency. You subtract it from 1. This entire expression represents the part that is not recovered, which is this, since number 1 also gave us this formula. So you raise this to N. And the same info you will place here. Your answer is N equal to 7.54. Now, if N is equal to 7.44, your efficiency will be 0.9999. If it's just 7, it will not reach this. So to ensure that you will really acquire or achieve such separation efficiency, then you have to use 8 extraction units. Okay, so 8 gid siya yung answer. So diri, wala ta naga-answer sang decimal, gina-answer ta ang next higher whole number. Even class, even if this is not, kung applyan mo blas ang mathematics, hindi siya ma-round off. Like even if this is 7.1, you will have to still answer 8. Because if it's just 7, it will not reach the efficiency that is stated. So then the next higher number should be your number of extraction units. Okay? Now, next. To plan a liquid-liquid extraction, we need to know the solutes distribution ratio. So this is something new. Solute distribution ratio between two phases. How does the solute distribute itself between the phases extract and raffinate? One approach to this is to carry out the extraction on a solution that contains a known amount of solute. So you have a solution having a known amount of solute. After the extraction, we isolate the organic phase, the solvent, and allow it to evaporate. Of course, it will leave behind the solute that it took out from the feed or extracted from the feed. In one such carried out experiment, 1.235 grams of solute, unknown ang identity, with a molar mass of 117.3 gram per mole, is dissolved in 10 ml of water. Now, your solute with this molar mass, with this mass, was dissolved in this much of water. After extracting with 5 ml of this organic solvent toluene, 0.889 grams of the solute is recovered in the organic phase. This is the recovered part. What is the solute's distribution ratio between the water and the toluene? The water is the raffinate because it's the water-rich layer as we refer to it. The toluene is the solvent-rich layer, which is your extract. Now, if we extract 20 ml of an aqueous solution that contains the solute, so this time you have this scenario that if you use 20 ml, not 10 ml of water, but 20 ml of this aqueous solution that contains the solute, using 10 ml of toluene, so increase ang toluene, what is the extraction efficiency? How many extractions will we need to recover 99.9 of the solute? Okay, so 3 questions in this case. One scenario, you've dissolved 1.235 grams of solute in this much of water using this much of toluene, and this is your recovery. This one is just the molecular weight of your solute. Now, what is the solute's distribution ratio based on this info? Okay, you don't work out the information on the next data. Then if we extract 20 ml, so this is L, your aqueous solution, your feed, L, in an aqueous solution that contains the solute using 10 ml of toluene. This is your B. So L is 20, B is 10. What is the extraction efficiency? So this letter B can be done with the previous examples that we have discussed. How many extraction will we need to recover 99.9 of the solute? This one can also be answered. So what's new here, not that quite new, is the how will the solute distribute itself in water in toluene? So this is in letter A. We call that the solute distribution ratio, or the one that is referred to as the distribution coefficient. So take note of this particular solution. You use the extracted amount of solute, the one that was uh, extracted by the solvent. In that case, that's the 0.889 grams. You use its molar mass. So then you will have moles, and then you multiply it with the amount of toluene that was used. Okay? Now, in the denominator, so this is your data in your V. So moles in V. Because this is the amount that your V has or was able to take out from the feed. In here, so whatever is the remaining that was not absorbed, that was not extracted by the V remains in your raffinate, the L1. So remember, you have 1.235 originally dissolved. So meaning, ang iban ato na sa inyo raffinate. So amo na ni nagkadto sa extract. So 1.235 minus 0.889, this is the amount that remained in the raffinate. Still using the molar mass. And this time, you make use of the 10 ml. The 10 ml of water because this is your water-rich layer already. Your feed is the one that leaves as your raffinate with the unextracted amount of solute. So that is why you had here 10 ml. This one is your extract, which is actually coming from your solvent, which is 5 ml toluene. So this is your K, 5.14. Okay? Now, that's your answer for letter A. For letter B, the solute remaining, kabalo na kamo sini because it's the same thing with number 1 and 2. You use 20 ml for L, you use 10 ml for V, and you use the K that you were able to determine here from letter A. So in cases wherein the problem does not give you the distribution coefficient, it's still possible for you to get that particular value as long as you're provided with this experimental data, because this one was carried out that way the distribution ratio could be determined. Okay, so you just use the 5.15. This is the 10 ml of your what is asked here, toluene, and 20 ml of your feed. And this is your solute remaining. The extracted is 1 minus this. So it's 72%. To extract 99.9, so this one actually is the 1 minus E. That is why you have only here 0.001. And we equated it to the same formula that was introduced to you a while ago. The L over KV plus L raised to N. So your N is 5.4. As such, well, you have to answer 6 here. So I did not place here 6. So to have or to achieve 99.9% of the solute recovery, you should have 6 extraction units in this case. Now, class, again, in all these sample problems, you are using fresh solvent. Whether you have a single extraction unit or several extraction units, this one is not, this particular formula is not used in an extraction tower wherein from the top, from the bottom of the tower, you have the solvent and then it flows counter current, the feed that goes down. So in this case, your solvent is already carrying with its solute as it goes up the column. Unlike this one that you have fresh solvent introduced to each of your extraction units. So that is why this formula is not being used in counter-current extraction, multi-stage extraction. This is also for multi-stage extraction, but it's like you have a separate compartment for each and a fresh solvent that is used to extract the solute in each of the extraction units that remained unextracted. Okay, I will go back to the slide. This one we're done. And we have efficiencies here. Okay. The reason why I place it in here, the efficiencies, is for your information only. Although if you're going to refer to the CMO, it's not placed in there that we're going to cover everything, including efficiencies for the extraction units. But just the same, if you would be asked where to find the formula in your handbook to solve such, you have these equations in your handbook. Though I have placed again here the 8th edition of your handbook. Okay, the HETS, how it's being used to solve for the z. There's a sample problem that I've discussed already, and it's already recorded how you use the HETS in determining the z. As for a formula available in the handbook to use, this is that particular equation, 15-57, making use of the HETS from a table also to determine the z. If you recall, you still need to determine the theoretical number of stages that you will multiply to HETS, which is an average of two values to get the Z as discussed. So this is the same equation that you have in your handbook. Okay, this ends the topic on extraction, which leaves me to ask you questions. If you have questions, Wednesday is your time to prepare for your quiz on Thursday. We'll have a quiz on Thursday. I will give it in the dry lab schedule. That way you will have enough time to prepare, because majority in the class except Justin will have their quiz also in kinetics on Wednesday. So your SEPA will be on Thursday and your kinetics will be on Wednesday. I will stop recording now.